representation based on Algebraic Hertzian construction and SYZ wave symmetry. So at the beginning, I will be slightly late, but later I will be more precise about the definition and the statement that I use. So in mathematical physics, people want to construct the anti-cell dual solution over R4, or if we fix a complex structure, so over C2. So this questions was solved by Algebraic Quiver Varieties. They tell us that these can be constructed using some linear data, which nowadays can be understood as quiver representation. The coherent sheaf come into this picture when Donaldson noticed that these are actually using these linear data. Actually, one can construct some free holomorphic vector bundles over CP2. This is Donaldson's result. Later, I will be more precise about all these relations, so on. And this result can be generalized. It's generalized by Nakajima. It showed that actually there's a 1-1 correspondence between free torsion-free sheaf over CP2 and such quiver representation. Yeah, for people who are interested in mirror symmetry, for example, if I know the mirror X, let's see, this is C2. In this case, C2, later it could be more. One can ask the following questions. We know that these are certain coherent sheaves, right? Then one may ask, what kinds of Lagrangians are mirrored to such coherent sheaf? Okay, are mirrored to such coherent sheaf? And what are the relations between these Lagrangian submanifold and quiver representation? And for people who are familiar with quiver representation, to talk about quiver variety or talk about quiver representation, we fix some dimension vector. So what does that mean on the Lagrangian side? And quiver representation also has some stability prediction. What does that mean on the Lagrangian side? Right? So there are a lot of questions that we can ask based on such construction. Yeah, it turns out that all this actually come from geometry. All these can be realized as Maurer-Cartan deformation space of some Lagrangian brane. So all these are Maurer-Cartan deformation space of some Lagrangian brane. Here I will be more precise. And one of our theorem is that in such setting, the Maurer-Cartan deformation space of a Lagrangian brane would be a Nakajima Quiver Varieties. Now, this is a bundle. In general, it will be a Nakajima Quiver Variety. Yeah, I will be more precise from now on. Okay. Yeah, now let me be more precise about the relation and the definition. So let me first talk about the relation between coherent sheaf and quiver representation. More precise about this relation. To do so, let's recall Nakajima's version's ADHM construction. I need a definition. So what is a free torsion-free sheaf?
Yep. So what's being mirrored are the entire moduli spaces.
Yes, these are moduli space of Lagrangians in some sense.
Right. Yeah. So we think of those as the analog of Yao, and that's what's being mirrored.
Yes. Yeah. Actually, in this case, it will be C2 and C2, so that hyperkähler rotates in some sense.
You're about to say more about quivers, but I'm interested in embedded quivers, quivers on ringed surfaces. Is that part of the story, or does that not enter into it?
Yeah, this is two dimension. If we go to one more direction up, that yeah, I mean in the general picture, if we into this, it's related. But today I will not. Yeah, I may not talk about that. Yeah. Thank you for the questions. Okay, yeah. Free torsion free sheet is a pair, so it's a pair. It's a pair such that this is a torsion free. Let's say a free torsion free sheet over CP2. This is torsion free. Frame means that we have a fixed trivialization at infinity line inside CP2. Because this is a torsion free sheet, it makes sense to talk about rank. It's free over a dense open subset, so we can talk about rank. Frame means that we have a fixed trivialization at the infinity. So R is the rank of this free torsion free sheet. Okay. Yeah, let me give you some example of this. So let's recall Nakajima's version's ADHM construction. Yeah, so okay. So let's recall, let me give you an example. How does the cohesion related to Quiver representation? So let's think about the RAM1 free torsion free sheet over CP2. So RAM1 free sheet. Let's see. Yeah. Up to isomorphism, such class actually is isomorphic to the torsion free sheet because we can restrict to the C2 is related to the torsion free sheet of RAM1 over C2. Okay. I forgot to one condition. Let's talk about the second condition actually tells us that the first class of the free torsion free sheet will vanish. So if we want to have a good moduli at the kinetic component, we may fix the second class of this. Let's fix it to be n. N is greater than 0. Yeah. So it's not locally free. In this case, if we consider RAM1 free torsion free sheet over CP2, after restriction, it corresponds to a torsion free sheet over C2 that has second number n. Actually, these are ideal sheet of n points. It's not really sure. Yeah. Why are these related to quiver representation? This is because if we take an ideal sheet of n points, because this is a phi scheme, so I will not distinguish the module and the associated sheet. So if we consider the quotient, let me write C2 as stack of C1, Z2. Okay. And then we can consider the quotient of this ideal sheet of n points, so we will get a vector space which is Cn. This is a algebra. This is a finitely generated algebra by Z1 and Z2, so we can multiply Z1 and Z2. This actually will induce two endomorphism of Cn. So find that we first had a Cn, and then we also have two endomorphism. Because Z1, Z2 commute, actually this will be the restriction on such endomorphism will tell us that B1 and B2. Furthermore, we also have a coefficient we had a natural inclusion here and then actually map to the portion. So we know that an ideal sheaf will also correspond to a linear map from C map. Well, let me call this map I. We know that this is a finitely generated C algebra. This means that multiplying Z1, Z2 sufficiently many times, actually we will get the surjection. So this actually corresponds to another condition of these linear data. Yes. In the quiver representation setting, it's called stability condition. It tells us that there's no proper subspace B that is B1, B2 invariant and contains image of R. Because if we multiply sufficiently many times, we should get the whole space. We should get the whole space. So Nakajima tells us that this actually is a 1-1 correspondence. So given the ideal sheaf, okay, in the original setting is rank 1 free torsion free shear over CP2. Actually, it corresponds to such linear data. This B1, B2, and I. And he showed that this is a 1-1 correspondence if we consider the correct isomorphic symmetons. This is 1-1 correspondence as set. Okay. Yeah. Actually, if we introduce the correct moduli functor, this is a quiver variety. This variety represents the corresponding moduli functor. This is Quiver scheme of n points over C2. If we introduce the correct moduli functor, this is Quiver scheme of n points over C2. And the n just corresponds to n points. Okay. Questions so far? Yeah. There are at least two ways to generalize such construction. One is that we can consider higher rank. This is just rank 1. Okay, this is just rank 1 free torsion free sheet, but we can do more. So we can consider free torsion free sheet of rank R over CP2. It also corresponds to some linear data, but this time we will have more error because this time we have more error, and the relation is slightly changed if we consider higher rank. Maybe it would be better to use another column. So we will have more error, and here will becomes R. So if we consider rank R, then this vector space will change accordingly. So the rank 1 case can be understood as a special case that J equal to 0, because if J equal to 0, we get back the original condition. So actually, this quiver variety represents the moduli space of free torsion free shear of rank R over CP2 that has second chain number n. Yeah, this is one way to generalize such a result. And Kurihama and Nakajima tell us that actually these constructions can be further generalized to so-called another way to generalize it is instead of consider CP2, we may consider other surface. So Kurihama and Nakajima tell us that the result can be generalized to ADE surface. Yeah, by ADE surface, I mean, yeah, given the finite circuit in SL2C, the portion may have simple singularity. And it admits a minimal resolution or a Quaker resolution. This is a variety, it's a resolution as a variety. For example, if we consider Z2 and add diagonally on C2, the resolution will be T star P1. be the cotangent bundle of P1. Yeah. So these spaces are interesting because for a lot of reasons, it's related to the 2D Mackay correspondence, no matter the right sense or the classical sense. And the result of Kohama and Nakajima tells that actually one can also perform the ADHM construction over such space. And the modalized space of free torsion free sheet over this guy can also be represented by some. It's also representable. It has 5 modalized space to be quiver varieties, but not this quiver, but some other quiver varieties. Yeah. So the key thing I want to give you a sense is that actually one can use quiver representation to study some coherent sheaf. For example, in this setting is free torsion free sheaf. And this gives us one important family that we can use, the relation between quiver representation and coherent sheaf. There are more actually, because if we are familiar, for example, if we are given a smooth projective variety, if it makes exceptional collections, then we know that the derived category is equivalent to the derived category of a past algebra. So in that setting, we also know that we can use quiver representation to study the coherent sheaf. More generally, for example, if a tilting bundle, then we also have such relation. This is what I want to talk about, the relation between coherent sheaf and quiver representation.
So how many nodes are in your most general query?
How many nodes? Oh, I see. Do you mean in the AD surface case or in
I'm just trying to understand. So you originally had a single node.
Oh,
B1 and B2. That was the old Nakajima story.
yes.
But you're generalizing this to 2 nodes?
Oh, no. I'm saying that if I consider the coefficient ring, I actually will have one more node.
Right, so you get a second. Okay.
Yes, and this node is called framing because it captures the information that the coherent sheaf frame at infinity line.
But that's it, it's 2 nodes.
Yeah, only 2 nodes in this setting. Yeah, and in the AD case, actually the number of nodes are equal to the corresponding alpha thinking diagram.
Yeah.
And if I consider the free torsion free sheet over the surface, I will have double nodes because for each node I also have a similar node called the framing vertices. Yeah. Thank you for your questions. So this is this case is 2 nodes. Now I want to talk about the relation between the Lagrangian submanifold and quiver representation. To do so, I want to introduce the work of Cheung. So there, the localized mirror construction introduced by Cheung and Lo. They tell us that every time we are given the Lagrangian immersion, L inside M, there's a way to assign a quiver. We can assign a quiver in the following way, that is for each irreducible component in the normalization. By normalization, I mean, for example, this is a Lagrangian immersion, we can consider the kinetic component in the domain. Their construction is the following: for each irreducible component, we assign a vertex. And if we consider the Foucault category, it makes sense to talk about. There are some choice of degree, but we can talk about degree 1 intersection point, degree 1 cell intersection point. We can assign an arrow. I will give you some. Maybe let me give you some example. For example, if I given an immersive figure, or pinch chloride, so algebraically, then write it this way. I will draw in this way. Yeah, if we use Arcaro-Joyce model, there's if we use Arcaro-Joyce model, the degree 1 intersection point will have some directions. In this setting, actually, these can be assigned to be degree 1. These are two different intersection points in the normalization because one is from North Pole to the South Pole, the other is from South Pole to the North Pole. So according to their construction, then the associated quiver of this would be we have one vertex, because in the normalization it's just S2. So we have one kinetic component, and we have two degree 1 intersection. So we get back a quiver that is similar to one in that setting. Okay. You may ask why we care about this quiver? This is because the path algebra of this quiver will capture the formal deformation space. It will be a path algebra. Path algebra. We need to notify AL. There will be a path algebra. In general, the deformation rate has some obstruction. This means that, here by deformation, I mean the following. So, I mean the deformation of the MK operators. So if we have a degree 1 element inside the Lagrangian Fourier cochain, we can use it to deform the A-infinity algebra. Use it to deform the A-infinity algebra. We can deform the MK operators, but in general, it may have some obstruction. And the obstruction would be some relation, would be the relation of this path algebra, would be the relation of this path algebra. The advantage of their construction is the following, is that if we they tell us that if we perform such construction, we will always have a function from the Fourier category of M to the DG category of such model. They call this localized Fourier function. Let me be more precise about, and let me justify why we get this name, localized Fourier function. This is because according to SYZ mirror symmetry, we know that the mirror manifold is conjectured to be the modi space of Lagrangian. Hence, one point in the mirror should correspond to a Lagrangian inside L. Therefore, the deformations of L would be a neighborhood of P inside the mirror. So in this sense, it's called a local piece of the mirror, as mirror. On the other hand, it also has some phase-focal condition. This is also reasonable because L is just one single Lagrangian immersion. It may not detect all. It can only detect the Lagrangian that intersect L. So they have some phase-focal property. So we call this a localized mirror function. Let me give you. previously maybe let me previously I write down I just draw an immersive sphere, but I didn't tell you how does it arise. So I have better explain why we get those Lagrangian inversion. And so to do so, I will introduce the main symplectic manifold that I consider in this talk. It's also related to our previous story. So let's consider the following symplectic manifold, which is a hypersymmetric inside D3. It's defined by UV equals to Z plus 1. Okay. And for some technical reason, I will require Z to be non-zero. This space makes a conic vibration by projecting to the last coordinate. So to visualize this space, we can imagine the following. So let's imagine this is the space, and I consider a puncture here. I remove the origin. So generically, if I fix a point on the base, if I fix Z, then I get a conic because it's just UV equals to nothing. So generically, we will have conic. But over -1, when Z equals to -1, it becomes UV equals to 0. So we get a singular conic. Furthermore, this space will make a Hamiltonian S1 action with the weight y-1, 0. This means that it adds on this by zeta UV, zeta inverse V, and Z. Okay. So with the weight y-1, 0, it induces a Hamiltonian S1 action. Use a Hamiltonian S1 action. And the moment map would just be 1/2 normal U squared sub norm V squared. They are interesting because actually it produced a Lagrangian torus vibration of this space. Because we can think in the following way. If we pick a circle on the base, circle radius R, okay, we can consider its pre-image in the total space. If we fix the moment level, for example, if I consider a point and fix a moment level, we will first get a circle. And if we do the parallel transport according to the symplectic connection, actually we get a torus. So over each one, we had an S1. If it goes around, actually we have a torus. Okay. So this actually gives us a Lagrangian torus vibration of M. So just map UV Z to the radius of the circle and the moment level. Because if we fix these two data, we get a torus. If we fix the radius and if we fix the moment level, which is the height, then we get a torus. So and the immersive sphere that I just draw actually is the pre-image. The origin is the pre-image of the origin. Because if the radius equals to 1 and the moment level equals 0, then we have the following picture. So let's say the yellow circle has radius 1. This is radius 1. If we fix the moment level 0, so generically we still have S1, but this S1 will shift into a point if it approach to the -1. So actually, the image of the origin would be the immersive sphere. because generically I am S1 and it's shaped to a point there. Why do we care about such Lagrangian immersion? Let me tell you some facts. Based on those facts, we can try to answer the questions that we asked at the beginning. So, this space has been studied by a lot of people. For example, Auru and Hong Kim Lau. So Hong Kim Lau were with this Lagrangian immersion. And they try to compute the formal deformation space of this Lagrangian immersion. Let me call this L. Previously, we know that if we perform the Cheung-Lau's construction, the formal deformation space would be a localized mirror. So they try to compute the localized mirror correspond to this. So they find that the formal deformation space of this L would be the foreign ring. So it would be the ring. So we recall that we know that the associated quiver is this, and we call this little x and little y. So originally it's just a free class algebra, but the obstruction gives us some relation on this deformation. In the end, deformation space will be the foreign. It looks complicated, but actually this is just the formal neighborhood of the xy axis. It's the formal neighborhood, the xy axis. And I write down a numerical ring here, but it's not very important in stuff. So what we had to know is just this actually contains the complex coefficient. It contains the Euro coordinate ring of C2 as a subring. We had to work with this guy and test this series because in the Fukara category it has some conversion issues. So we had to do with this to deal with the conversion issues. Okay. But if we restrict to the subcategory, or if we restrict to a neighborhood of this L, or restrict to the subcategory that has no conversion issues, actually we had a function. If we restrict to that, we can restrict the coefficient, and the geometrically it means that we do the extension from the xy axis. This is a formal neighborhood of xy axis. If we restrict to the subcategory that has no conversion issues, this actually can expand to the whole C. So we get a functor from the category and if we consider the full subcategory that has no conversion issues, actually get a functor to the DG category of CXY motion. And this can be understood as the DG enhancement of Bergen shape over C3. Yeah. So if we're back to the beginning, we find that the free torsion-free shift over CP2 up to isomorphism. If we restrict to C2, we get a torsion-free shift over C2. So by this, I mean they correspond to torsion-free shift over C2 that has natural extension to CP2. And now, this localized functor tells that C2 is somehow a mirror of this space. If you think about this actually isomorphic to C2 in some sense, because that is determined by U and B. So with such explicit mirror functor, we can start to answer the questions. What are the Lagrangian that mirror to free torsion C2? What are the Lagrangian mirror to free torsion C2? Because we had a very explicit description of how they correspond. So we can start to answer this question. what are these Lagrangians that mirror to free torsion free sheet? And the answer is that actually, in this setting, the free torsion free sheet would be a union of the Lagrangian section and the Lagrangian immersion, that immersive field that we consider. Yeah, let me justify why this should be the right answer. Okay. But to do so, I have better give you a sense of how does the Lagrangian section look in this setting. Yeah. So let me first explain the Lagrangian section and then give you an intuitive representation why this should be the right answer. These are the Lagrangian mirrors of free torsion free sheet. So yeah, to get a Lagrangian section, one can consider the following paths in the base that go to infinity. And over each point, we pick a line. This purple line. So we may find that it hits every torus once. If we do parallel transport with respect to the synthetic connection, so over each point we get a line. So in the end, we get a Lagrangian that diffeomorphic to R2. And by construction, it hits every torus once because, yeah, if we stare at this carefully, we find that it only intersect the circles at one point. The corresponding circle at one point. So this is a Lagrangian section. Let me not mention some technical detail here. So I will call this Lagrangian section. Because we find that in general, the framing Lagrangian, the Lagrangians that are mirrored to the framing condition would always look like this. Yeah. So let me briefly justify why this should be the right answer. Let me give you an intuitive proof why this should be the right answer. Intuitive justifications. This is not a rigorous proof, but I like it. It tells us how to think about this question. So to do so, maybe let's come back to the ideal shelf 1 point. Let's come back to free torsion free sheet that has RAM 1 free torsion free sheet and the ideal shelf n points. In this case, let's consider ideal shelf 1 point. So we know that if fitting to a short is a sequence, it's the ideal sheet to the structure sheet, and then to the skyscraper sheet. So according to homological mirror symmetry, the derived category of coherent sheet is equivalent to the derived Foucault category as a triangulated category. Hence, it should preserve the triangulated structure. But on the other hand, by SYT program, we know that the trivial line bundle should mirror to a Lagrangian section. And the skyscraper should at one point should mirror to a fiber of the Lagrangian torus fibration. Hence, one should expect that certain union of these two is mirrored to ideal shelf 1 point. So in other words, they should mirror to free torsion free sheet over CP2 in some sense. So one should expect certain union of these L and F should mirror to ideal shelf 1 point. And the aside is the following. By that, a good arrangement of the blackboard. So let me get some space here. The aside is the following. if you think about how does a Lagrangian section union with L look like, so in a 3-dimensional, this is 4 dimensions, so in 3-dimensional, it roughly look like this. This component is my F. This component is my F. This component is my F. So if we think about the associated quiver, yeah, so you may find that in the normalization, this time we had 2 components, or we should have 2 vertex. And as before, we still have these 2 degree 1 intersection points. These correspond to 2 arrows with x equal 1. But because now we have 1 more component and it intersect with L transversely, actually we have 2 more intersections. So it corresponds to 2 more arrows in the cases. So this, so we find that the associated quiver is exactly the quiver that we mentioned in the ADHM setting. And this is mirrored to this vertex, we call it the framing Lagrangian. And one can also perform the calculation and compute the deformation space of this. Okay. Actually, we find that the deformation space of L union with F, okay, I will call it free Lagrangian, is a path algebra of this quiver. So we call this Q frame, this KQ frame, quotient singulation. So if we perform the Chorlin-Laws construction, we find that the obstruction equation is exactly correspond to the equation that we write down at the beginning. It's exactly the equation to define the related quiver variety. This is the complex moment equation of the quiver variety. It's also the one that I mentioned at the beginning. So here we come to our first serism. Actually, this is just an intuitive verification. We find that all the data match. So actually, if we show that if we use this to transform the union, okay, let me call the union to be L frame. I forgot one more thing. So actually, we can perform more calculations. So this is formal deformation space. This is like this is just algebra. So if we equip each irreducible component with some trivial vector bundles, that's denoted by let's equip L with the rank of this trivial vector bundles. Okay, I would say this is the trivial vector bundle in the normalization of this L. So the rank of this vector bundles actually equals to I want to say that the rank of this bundle actually will correspond to the rank of the representation, the dimension vector of the representation. And we also compute the deformation space of this Lagrangian immersion together with a vector bundle. We find that it's the following quotient step. So if we perform computer deformations, and we use the same notation. So actually, it's a representation of this quiver. Space. If we compute the deformation space of this together with a true vector bundle, actually, it will be the following Gaussian stack. The rank of the bundle over the framing, for example, this is a bundle in the normalization. So over each component, they could have different rank. I mean, if the rank equals to R, and the rank of E equals to L equals to N, then the corresponding representation would have Cn over here, C1 here, and it satisfies the relation that we write down before. And formation space will be this Gaussian stack. We had a stack because we didn't fix any stability condition. This is exactly what we mentioned at the beginning. In terms of this observation, our strategy here is first we borrow the stability condition of a quiver representation and define a tautological stability condition and later analyze its geometric meaning. Actually, this stability condition also fit in the XYZ setting in some sense. The corresponding stable element can be identified as the deformation parameter of some special Lagrangian. So this is also expected in some case. So we will first borrow the stability condition and define what is a stable free Lagrangian brane. And then we show that under the functor we mentioned before, this has cohomology to be a torsion free sheaf. This is a complex of CXY module, and its cohomology is a torsion free sheaf. It's a complex cohomology. And if we have, and this complex actually tells how to do the extension. So if we homogenize the complex, we get a free torsion free sheaf over CP2. So, the upshot is we find the Lagrangian that corresponds to the free torsion free sheaf that we mentioned at the beginning. And furthermore, we can produce the free torsion. We can also produce the free torsion free sheaf over ADE surface. The same. ADE surface. We can also produce free torsion free sheaf. To be more precise, let me draw more picture and talk about what do we do for ADE surface. For the construction, over AD surface, we need a construction called plumbing. So the plumbing construction is the following. If I given a graph or a diagram, for example, a phi AD diagram, for example, a phi A1, this is phi A1. There's a way to construct a sympathetic manifold together with some interesting Lagrangian immersion. It's called a plumbing. So it's the following. So for each vertex, we can assign a Riemannian manifold. In our setting, we assign S2. We assign the 2 sphere. So for each vertex, we assign 2 sphere. And for each edge, we assign a sympathetic morphism to glue the corresponding unit conormal bundle. So we assign gluing between the unit conormal bundle. Yeah. For each edge, we assign gluing. To talk about the gluing, we have to pick some base point and open the groove near the base point, and then we glue the corresponding sympathetic manifold in the following way. So this is a sympathetic morphism. So after gluing, we get a sympathetic manifold. And this is unit conormal bundle. So we can do the completion along the cotangent direction. So in the end, we get a new real manifold. So after completion, we have a new manifold. So in this setting, for each vertex, we assign a sphere, and for each edge, we glue it. So in the end, we will have a pattern like this. And the sympathetic manifold M will roughly look like the cotangent bundle of this. Roughly. It's the cotangent bundle of this guy. The zero section will look like things like this, and for they have transfer intersection for these. So okay, because of time, let me denote this Lagrangian by L again, like by dou L. So we find that if we do such construction, we get a new room manifold, and the zero section may have some pattern like this, some Lagrangian submanifold that has pattern like this. You may notice that there are some compatible gradings such that these are all degree 1. So let me call this x1, x1 bar, and y1 bar. Okay. So if we perform such construction, every transfer intersection point actually produces 2 arrows, one and in reverse direction. So actually, given any graph, and the associated quiver, we can perform plumbing construction, and then we get a Lagrangian immersion inside the sympathetic manifold. The associated quiver this zero section is actually the doubling of the graph. For example, in this setting, just like taking the dual graph, the corresponding graph is this. We also compute the deformation space. deformation space of this Lagrangian immersion is a Hertzian algebra. Hertzian algebra of this quiver let me call this quiver Q. The Hertzian algebra of this quiver Q. Oh, 1 minute. Let me.
It's just is like for general quiver, not just any type.
Oh, you're right. So the underlying graph need not be a phi AD. So for general graph, if we perform such construction, the deformation space will always be the Hertzian algebra. Okay, thank you for the questions. Let me finish the story. So, yeah, and okay. So, and the framing Lagrangian of this setting would be some cotangent fibers. So, if I denote L, move L usually with some cotangent fiber. They will satisfy some technical conditions, and we will call them, so if they satisfy some technical condition, we call them framing Lagrangians. So in this example, the cotangent fiber look like this. So cotangent fiber at some point like this. So if we do such union, actually the associated quiver will be the free double quiver. These two anchor vertices correspond to the cotangent fiber. And the deformation space of this would be a free version of the Hertzian algebra. Free. And the corollary is that if we equip them with some bundle, then we get a quotient that and if we fix a linearization, we get a Nakajima Quiver Variety. Let me fix frame. So if we consider free Lagrangian, we have a corresponding quiver, we call it Q frame, and there will be a free Hertzian algebra of this Q frame. And the Maurer-Cartan deformation space would be a Nakajima Quiver variety of this Q frame, together with the dimension vector to be the rank of this bundle. If we fix our linearization. Yes. This is the my book. Okay.
Yeah, so just to follow up, so help generally, you can take any graph, you're replacing the nodes of the graph by Lagrangian X2s.
Yes, after the construction, you will get it because it will be a zero section of some cotangent bundle, so they are Lagrangians. So yeah, as you mentioned, for each vertex, in the end, we get a Lagrangian. Yeah,
and then deformation. So the pre-projective algebra of the quiver is being constructed and identified.
Yeah.
Deformation.
Yes, it's directly with the deformation space.
Okay.
It's a part. Yeah. This is. Yeah.
So what if you have a super potential?
Yeah, you're right. Actually, in this setting, we don't have all the super potential equal to 0 in this setting because we are only this Liouville manifold. There are only real 4 dimensions. Because we assign each vertex only a twofold, so in the end it's real 4 dimensional, so the super potential equal to 0. But if I get some real 6-fold, complex 3-fold, then we will have super potential. then the deformation space actually will be the Jacobi ring of that, of the associated quiver potential. So they are related to some Calabi 3. So yeah. So far for this dimension, we only had a parse algebra that has no super potential. But if we go to higher dimension, we will have quiver and we will have quiver potential.
But there's another thing you can do in this dimension, right? You're dealing with the Siu-Cheong gamma.
Yes.
You could globalize to the K3 case.
Yeah, that's why I want to ask you before. Yeah.
We should talk about it.
Yeah, because this is like the local part of some.
Yeah, exactly. And you have nice results literature on moduli spaces with sheaves on K3s being themselves.
Yes. Nakajima in the book it also said that already. Yeah. Yes. So yeah, we are also thinking how to glue this guy whether we can get the torsion ratio of K3. Thanks.